Hello guys, welcome back to Maison African Motives, still working on industrial electronics N2. In this platform, we have got the question paper, which is which was written in March 2023. Okay, so that is 2023 X paper from 9 to 12. So that was what we have. We are given drawing instruments and non-programmable calculators may be used, and also what is important, the instructions. So we shall quickly rush through so that we see what you're given. So it was a 3-hour paper. Given the instructions, the most important part is that you're supposed to number the answers according to the numbering system used in this question paper. Okay, and also to start each question on a new page. That one, guys, we are used to that. All right, so let us quickly rush through the questions that we are given. Question number 1, we are given to refer to the circuit diagram below and answer the questions that follow. All right, so this was the circuit diagram, which is a DC circuit. From this circuit, we are asked to calculate the total resistance in the circuit. So let's just analyze the circuit before we attempt the question. We see that we have got a voltage source with a positive and negative in this case, so which means we shall have the total supply of current in this case. So here we shall have the total current that is going to flow to this point. And at this point, it is going to branch into 2 branches, that is in this one and also this branch here. So you shall name these currents according to your way, whether it's current 1 or current 2. So here I'm going to name this as current 1. And this is going to be my current 2. So it depends with your numbering system, all right? Then to these resistors in parallel, we've got R5 and R6 in parallel, then connected in series to the 4-ohm resistor and so on. All right, so how can we calculate the total resistance, guys? Okay, that's 8 marks for that. Okay, anyways, so you're going to see that here we have got R5 and R6 in parallel. So we can start by combining these 2 resistors in parallel. All right, so this is question 1.1. All right, so we shall start with the resistors in parallel. Just combine them. We know that resistors in parallel is going to be the product over the sum. So we're going to have the product of R5 and R6 over the sum, that is R5 plus R6 in this case. All right, so this is going to be R5, which is 6. So that's 6 times R6, which is 4. Everything over 6 plus 4, which is the sum of the 2 resistors. Okay, so if you are to combine this properly, you're going to obtain something like 2,4 ohms, which is the parallel combination of these 2 resistors. Okay, so now that we have this total resistance for the parallel combination, we can redraw our circuit to see how it is going to look like. Yes, you can just even combine and see, but for me, it's best to just draw the circuit. So we've got the series resistor on a parallel, on a source, this from the source that we are given. So which means our circuit is going to be like this. Now, remember, we had a resistor here of R1, which was 7 ohms. So this was R1, which was 7 ohms. And we have got R2 and R3 and R4. So these 3 resistors, they are going to remain as they are, R3, R2, and R4. All right. So we are going to have here, there was R2. All right. So here we had R2 in this case. So I want you to see how it is going to look like. And here we had R3. This was our R3. This was our R2. And here we were given R4 like this. All right. So these are the resistors that we are given originally from this path. But if you have to check here, we combined these 2 resistors in parallel and we got 2,4. So this is now a single resistor. We combined this. So we are going to represent this as a single resistor now. So we are going to have RP like this. All right, so this is our RP. And remember that RP was equivalent to 2,4. So this is 2,4 ohms from here. RP is 2,4. R4 was equivalent to 8 ohms from the diagram. R3 was equivalent to 10 ohms from the diagram, all right? And also we are given R2, which was equivalent to 24 ohms from the original diagram. And also here we've got our VT. So the currents, they are not going to change. Here we're going to have our total current and so on. This part is not going to change. I'm not worried about the current. I'm worried about how the circuit is going to look like. So from this presentation that we see now, it's we are going to see that we are now having R3, RP, and R4 in a series. So we are going to combine these in a series. So that means we are going to calculate RS in this case. So we've got a series combination of R3 plus RP plus R4 in this case. All right. So that means our RS is going to be, we add this R3 is 10 ohms plus RP, which is 2,4. Sorry for that, plus 2,4 plus R4, which is 8 ohms. All right, so this is what we have. So we've got our RS. So if you combine everything, we are going to obtain 20,4 ohms. All right, so this is when we are combining this part here, R3, RP, and R4. Take note, the R2 is not in series, this one. These are the three resistors in series. They are affected by the same current of I2. R2 is affected by current I1. So these are not in series with R2, but in parallel. So meaning to say, your circuit after this, it is going to look like this. I just want you to get used to this concept of redrawing your diagram so that it can help you a lot. So now if you are to check, you are left with R2, which is here. This is where we have our R2 like this. All right, we have got R1 and R2, but we combined these three resistors and they gave us 20,4, which is in series. So we are going to have it as a single resistor now. We combined this, so it's now a single resistor that you are having of RS. So this was your RS, which is 20,4 ohms, all right? And here we were given originally R2. We didn't affect this. We never worked with R2, so it is going to remain as it is, which is 24 ohms. R1 also is going to remain as it is a 7 ohms, and definitely your VT and your currents. This is your total current. This is the branch for I2. This is the branch for I1 like this. Okay, so if you redraw like this, it's going to be easier for you to see, okay, now at this stage, what are you going to do? You can see that these two resistors that are left here, they are in parallel. So we have to combine them the same way we did on this parallel. So we can say that since we are now having a second option or a second parallel circuit, we can just say this was our first parallel combination, this one. So we are now having a second parallel combination in this case, which is of R2 and this RS. So that means our second parallel combination from the product over sum, that is going to be R2 times RS over R2 plus RS. Okay, so let's combine and see what you're going to obtain in this case. R2 is 24 ohms, so that's 24 times RS, which is 20,4, so that's 20,4, everything over the sum. So that is the addition. You're going to add the two. All right, so if you combine everything from this part, we are going to obtain 11.07. So this is going to be 11.027, sorry, 11.027. So this is the second parallel circuit that we combined together. So meaning to say, after combining these two, we are now just left with a proper series circuit, because this is going to be your R1. You combined these two resistors and you obtained a single resistor like this. So it's now a series circuit. This is our RP2, which is 11.07. So that was, 11.027 ohms. And this is your R1, which is 7 ohms. So as you can see, guys, we are now left with a proper series circuit where you can combine everything. So therefore, our total current, our total resistance, sorry, is going to be the sum of the two, because this is a series circuit. And remember, in series, you add. So this is going to be R1 plus RP2. That is our RT. The total resistance is going to be 7 plus 11.027 ohms. All right, so let's just leave this. We'll write it on our final answer. So RT representing the total resistance in this case was going to give us something like 18.027 ohms. All right, so that was going to be your total resistance for the given circuit. All right, so I just hope the steps were clear. These steps were clear, so you just have to follow these steps, guys, in order for you to calculate the total resistance depending with the circuit that you're given. So it depends with the circuit that you're given originally. All right, so that's what we had. 8 marks for that. All right, 1.2, calculate the total current flowing through the circuit. So the total current, that is the total voltage over the total resistance. So we can get back here because we have got our total resistance. In this case, we can calculate our total current. So that's 1.2. So 1.2 total current is equivalent to the total voltage, which is VT over RT. So the total voltage, remember from our circuit in this case, our VT, okay, I didn't indicate this, but from the circuit, okay, we can take it here. That is our VT is 48 ohms from the diagram here, 48 volts. Sorry for that. So this is going to be 48 volts in this case. So we are going to divide 48 divide by the total resistance of the circuit, which is 18.027. So that's it, guys. Make sure that you use your calculator properly. This was actually going to give us something like 2.66 2672 and so on, which is going to be 2.6 round off. This is going to be 3. So that is the total current measured in amps. Remember that current, guys, is measured in amps. So that was question 1.2 for the total current in the circuit. Let's check what we have on the other part of the question, which is on question 1.3. Now we are given to calculate current I1 and I2, okay? Current I1 and I2. So for current I1 and I2, it depends with the presentation that you indicated from your diagram. Okay, as for me, this is my I1 and I2. So it is going to be easier for me if I take it from this diagram. That's you see the issue, guys, of rehaving these diagrams. If I can get back to this diagram here where we simplified on this stage here, all right, we can actually understand that. Okay, let me remove this part. Okay, okay, it's fine like that. If you are to check here, we are given the total voltage. Remember your total voltage, which was 48 volts. And this is the total current flowing into the circuit. The total current, which is of 2.663 amps. This total current is going to branch into two, I1 and I2. So this is where we can determine our I1 on this circuit where we have combined this to be a single circuit. So from this part, we can understand that from our current divider rule, the current flowing through, okay, so this is 1.3, the current flowing through resistor 2, which is I1 in this case, is you are going to use the opposite resistor on top. So it is going to be RS over the sum of the resistors. So I1, you use the opposite resistor on top over the sum of the resistors. So you add R2 plus RS times the total current, which is branching into these two branches of I1 and I2. So you multiply to the total current in this case. So this is your current divider rule. All right, so from our current divider rule, we can see that our current I1 is going to be RS, which is 20.4. So that's 20.4 over the sum of the two, which is 24 plus 20.4. So that's 24 plus 20.4 times the total current, which is 2.663 amps. All right, so you're going to obtain I1 in this case. Okay, so that's your current divider rule, guys, meaning to say we are going to obtain our I1 as 1,224 if you round off properly in amps. Okay, so that is what you have. So that means for I2, for us to have I2, all right, sorry for that. For us to have I2 in this case, we are going to apply the same concept, okay? I2 is in this branch with RS. So you use the opposite resistor on top. So the opposite resistor is 24, which is R2. So your formula is going to be I2 is going to be the opposite resistor, which is R2, over the sum of the resistors, that's R2 plus RS, times the total current. Or you can simply subtract, since we understand from our Kirchhoff's law that the sum of current into the circuit is equal to sum of current away from the circuit. So since we have got I1 and the total current, you can subtract to find I2. It's simple like that. Or you can use this current divider rule again. That means your current I2 was going to be R2, which is 24. So you've got 24 over the total of the two resistors. That is 24 plus 20,4 times the total current, which is not going to change. That's 2,663. All right, so that is going to give us current 2 in this case, okay, which is, if you simplify properly, rounding off to 3 decimal places, this is going to be 1,394 and so on. So this is, if you round off, it is going to be 39 amps to 3 decimal places. So that was our I2. All right, so that is the application of the current divider rule, which is one of the, most important part that you can actually work with in a simplification. So like I said, to find I2, you could have even applied the other way around to say that the sum of currents into the circuit is equal to the sum of current away from the circuit from your Kirchhoff's law. All right, so then on 1.4, we are now asked to calculate the voltage drop across R5. Okay, so we need to calculate the voltage drop across R5 in this case. All right, so how can we calculate this voltage drop across R5? This is where we have our R5 in this case on this path here. This is where we have our R5. So we need the voltage drop across this this point. Okay. There are so many ways that we can apply. If you are to take note here, guys, RP is part of this voltage I2, or of this current I2, sorry. So that means we can actually calculate the total voltage for the parallel circuit. Remember, this is a parallel circuit that you have here. And in a parallel circuit, we know that voltage is the same. So if we can have the voltage drop across this part, that means we have the voltage across the 5 ohm. All right. So meaning to say, we can calculate, we have already the total for this, the total resistance for the parallel circuit. All we need is the what? Is to multiply by the current, which is I2, just like that. Okay. So that was another option that we could have used. RP in this case, this one for 6, we need this one for 6, and for the first one that we calculated here, if you check here, the first parallel combination, it was of 6 ohms and 4 ohms. Okay, the question is R5, yes, R5, which is our 6 ohms, yes. So which means we are having a parallel combination here. So what are we going to do? We are simply going to calculate the voltage across that parallel combination of 2,4. So you can even calculate it here. If you still remember your currents, guys. So that means the voltage across R5 is the same as the voltage across the first parallel circuit. It is the same because it's a parallel circuit. So voltage across a parallel circuit is the same throughout. So this is going to be the current I2. Remember, it is the current times the resistance that can give us a voltage, and I2 is flowing, affecting this parallel combination. If you are to check here, this is your I2. It is going to be part of these two. It is going to branch into these two, but it is the one that is affecting the total of these two resistors. So you multiply these two, that is I2 times the total for the parallel combination, which is the first parallel combination of 2,4. Okay, so I2, we calculated I2 before. If you check here, we are given our I2. All right, where is that I2? Here. All right, our I2, we calculated it was 1,439. Okay, 1,439. So this is what we are going to do. 1,439 times the 2,4. All right, so I2, we are going to multiply 1,439 times RP1, which is the parallel combination of 2,4. So guys, you have to be very, very careful dealing with this typical question to say a parallel combination, the voltage is not going to change. All right, the voltage is going to be the same. We are going to have the same voltage. All right, so meaning to say, if I calculate the voltage across the R5, I'm calculating the voltage across the parallel combination. All right, so this is going to give us 3,453, 6, and so on, which is going to be 3,454 volts, like that. So that was how you could have calculated the voltage drop across resistor 5. It's a parallel combination. Or you could have used current divider rule. You calculate the current across R5, then you multiply it to the resistance. Yes, it was going to work, but it was going to be a lot on that one. Okay. Then we are asked in this case to define the term volt. Okay, what is the term volt? And okay, so here volt, guys, we know that if you are measuring voltage, that's the unit of what? Of voltage. So this one is simply is the unit. So it is actually the unit of electrical, the unit of electrical potential. All right, that is the electrical potential, which means we are talking about the voltage in this case. That's the unit of what? Of voltage. Voltage is measured in what? In volts. All right, so that was the question, guys. On question number 1, carrying a total of 20 marks. Okay, question number 2, we are now given, that was a question on AC theory. And that's again 20 marks for this one. So we want to see how we're supposed to answer this typical question. We are given a coil with an inductance of 3 Henries and resistance of 700 ohms is connected to a 200 volts, 150 hertz AC supply. Okay, so this is what we have. We can just make a simple circuit to represent this coil that is being connected to a resistor. So we have got a coil in this case and a resistor. So I'm going to put a resistor here and a coil. So okay, just to make it a proper circuit. Then we are given in this case that it's an AC supply that we are dealing with. All right, so the resistance of this coil that we are given, it has a resistance of 700 ohms and the coil is 3 Henries. Okay, so this we have got a resistance here of 700 ohms and the inductance is 3 Henries. So given the voltage source of 200 volts and the frequency in this case of 150 hertz, this is the other information that we are given here, 150 hertz and the 200 volts for the what? The 200 volts for the voltage and the frequency of 150. Okay, so that's the second. So the first question on 2.11 was to calculate the inductive reactance of the coil, and that's 2 marks for that. All right, so here, even without a diagram, you can even answer this question, but just to understand what you are doing, that's why we are having this diagram. Okay, so 2.11, the inductive reactance, that is XL, is equivalent to 2 pi FL, which is, you're supposed to understand your formulas, guys. So this is 2 pi FL. So XL, which is going to be 2 pi times the frequency of 150 times the inductance, which is 3 Henries in this case. So you can combine this direct from your calculator. That is going to give us 2827, 4333 and so on. So if you round off these to 3 decimal places, this can give us 2827, 433. All right, so this is going to be 4,33. These three cannot change the other one. So that is what you have in ohms. All right. The other part of the question, which is 2.12, the impedance of the circuit, and that is 3 marks for that. So the impedance, remember, this is an AC circuit. We do not talk about resistance. We talk about the impedance of that circuit that you're given. So the impedance of the circuit given from the formula, that is Z is equivalent to the square root. Also in your formula sheet, you're given this formula, that is R squared plus XL squared, because we have got a resistor and we have got an inductor. So we're going to use R and XL. If it was a resistor and a capacitor, it was going to be XC, but here we are dealing with L. So that is the square root of the resistor. R squared resistance, it's 700 ohms. So this is going to be 700 ohms plus XL. XL is this one that we calculated now, which is 2827,433, everything squared like this. All right, so you're going to calculate the square root of this. That is your Z, which is the impedance. All right, so this was going to give us 2,912,795 ohms. So impedance is also measured in ohms. All right, so that was question 2.12. The value of the current through the coil. Okay, so we need the current, which is the total current. So since we have the impedance, which is representing the total impedance or the total of the circuit, so we can calculate the total current in this case, which is the current into the coil. So that is the total voltage divided by the total impedance. And we have got a voltage of 200 volts. And we also have the impedance. So this one was simply dividing 200 divided by the impedance of 2,912,795. That is going to give us the total current of the circuit, or the current flowing into the coil, which is going to be something like 0,06,866 and so on. So you can change it to 3 decimal place, which is going to be 0,0687. In this case, is it going to be, okay, that's 0.9. Okay, so this is going to be 9 to 3 decimal places here. Or you can round off even, or you can just put to milliamps to say your total current in milliamps. That is going to be 3 decimal place, 1, 2, 3, which is going to be 68,66 and so on milliamps if you want to convert to milliamps. Or you can just write it direct, 0,069 amps. All right. So that was the current flowing through the coil, or current through the coil. All right. Then on 2.14, the phase angle between the supply voltage and the supply current. Also, this one you are given on your form, or in your formula sheet, the formula for calculating the phase angle, which is theta. That theta is equivalent to arc cos resistance over the impedance. So this is an advantage to say we have this on our formula sheet. So that's theta is equivalent to arc cos resistance over impedance. We have the resistance from the diagram here, or from the information of 700 ohms. We calculated the total impedance. So here, which is our Z. So we can substitute and calculate our phase angle. That's arc cos resistance of 700 over the impedance, which is 2912,795. All right, so this is going to be our phase angle theta. That's 76,09463, which you round off to 3 decimal places is going to be 76,095. The 6 is going to change 4 into 5. So that's it in degrees. So that's your theta. All right, just like that, guys. Okay, 2.15. Now draw the impedance phasor diagram. Okay, we need a phasor diagram for the impedance. All right, take note here, we are dealing with an RL circuit resistor, resistance and impedance. So our impedance phase angle is supposed to be like this. Remember that L is going to be on top in this case. So we are going to have it, okay, this one does not affect. Okay, so this is going to be your resistance in this case from the current side, and we have got our XL. Okay, so remember that the impedance is the phasor sum of the two. So the Z representing the impedance is going to be in between like this. Z is the phasor sum of the resistance and the inductive reactance. So that is what you're going to have in this case. And this is your phase angle, which is theta. So you can write the values. You know that your R is equal to 700 ohms. You know that your XL, you know your Z. You can write these values. Your Z in this case was 2,912,795, your XL. So you can even write these values. But what is important is that your diagram is going to look like this. Okay, so that was your question 2.15. All right, so be very careful, guys, with your information that you're given. All right, so the other part of the question is now on 2.2. Name 4 conditions that exist in series RL circuit at resonance. Okay, that is a circuit at resonance if it is a series RLC circuit. Okay, so the conditions for a circuit to be at resonance for series these ones. We are going to have our circuit is going to be resistive. So the circuit is resistive. Okay, so the circuit is going to be resistive. That's number one. Number two, the current and voltage are in phase. So current and voltage are in phase. In phase, that was another answer, which is very, very useful. Also, current at that state is maximum. So current is maximum. All right. Then another thing was Z, which is the impedance is equal to the resistance, like what we saw previously. Sorry. We never did this question. We never did a question in series. Sorry. So that Z is equal to R and is a minimum, and this is going to be minimum and is a minimum. All right, so that is what you're going to have. So which means we're going to have the minimum impedance. Remember, we calculated before the impedance by finding the phasor sum. So if you see that this is a bigger value, but now if we say Z is equal to R, Z is now, when Z is now equal to 700, you see that that is going to be our minimum impedance ever in that circuit. So that is how these are the conditions actually that you have if whenever you are dealing with a series RLC circuit at resonance. Okay, so let's check the other part of the question, which is question number 3 in this case. All right, is that so? Oh, I left another part, 2.3. Okay, I left this part. Calculate the resonant frequency, okay, of a series RLC circuit that consists of a 10 nanofarad capacitor, a 10 millihenry inductor, and a 500 ohm resistor. Okay, so this is 500 ohm resistor that is connected to a 200 volt AC supply. Calculate the resonant frequency. Okay, so we know that the resonant frequency is given by the formula that is FR. So 2.3 resonant frequency FR is equivalent to 1 over 2 pi the square root of LC. That is, the resonant frequency is going to be 1 over 2 pi times the square root of, you simplify your L, which is the inductance. In this case, our inductor is having 10 millihenries. So that's 10 times 10 to the power of minus 3 milli times 10 to the power of minus 3. Okay, times the C, which is our capacitor. The capacitor in this case is got a capacitance of 10 nanofarad. So nano, that's 10 times 10 to the power of minus 9. Nano to the power of minus 9. Okay, so here we are supposed to simplify this direct from our calculator. That was going to give us 15,915,494 hertz. So it's a resonant frequency measured in what? Measured in hertz. So that was what we had, guys, from question number 2, having a total of 20 marks. All right. Yes, that's what we have. Question number 3, we are now given 3.1, make a neat labeled drawing showing the construction of a moving coil meter, and that's 5 marks for that. Okay, so a moving coil meter is going to be like this, guys. Okay, so that is what we have on a moving coil meter. So the most important stages for you here to show is the scale. All right, so make sure that everything is properly, the points are properly indicated. Okay, the control, the magnetic field, the coil, the pointer, or the needle in this case. So this is where you're going to obtain your marks from. All right, so that was what we had in this case. Let's get back to the question and see. We are now given, name 2 ways in which damping can be obtained or carried out in measuring instruments. Okay, which ways can we have damping? Okay, so we have got mechanical damping. All right, so we have mechanical damping. All right, we also have electromagnetic damping, magnetic. All right, electromagnetic damping. All right, so if you've got any other ways or options that you know, guys, let's list down answers on the comment section so that someone can be assisted from that information that you are helping on the comment section. All right, 3.3, we're now given a measuring instrument is a full scale deflection of 1 milliamps and internal resistance of 100 ohms. So this is a measuring instrument, which means we are dealing with the meter in this case. So the values that are on the meter, we are given a current of 1 milliamps in this case. So this is question 3.3. Okay, so you've got the current on the meter of 1 milliamp, and we are also given the resistance on the meter, the internal resistance of the meter of 100 ohms. So that is what you are given in this case from this meter. Then after this information, we are now given on 3.31 to calculate the value of a shunt resistor. Take note, you are given, it's a shunt resistor, which means we are talking about a parallel circuit in this case, to enable the meter to measure 10 amps in this case, which means this is your shunt current because we're talking about a shunt resistor. So that means we have got a shunt current of 10 amps in this case. So given a shunt current of 10 amps, what is going to be the value of the shunt resistor? So that was the question. Okay, so we know that in a shunt circuit, these two, they will be in parallel. Okay, so in this case, we are going to have a circuit like this. Remember, guys, in a shunt, that is going to be your meter in this case. Then we have got your shunt resistor in parallel like this. So we know that the voltage across the meter is actually equal to the voltage across the shunt resistor. So using this information or using this formula, we can take advantage to say the voltage across the meter is equal to the voltage across the shunt, and the voltage across the meter is the product of these two, current times resistance. So that is current across the meter times the resistance across the meter. And across the shunt, we've got current and resistance. That is current across the shunt resistor times resistance across the shunt resistor. So that means we can calculate the resistance across the shunt resistance. Since it is the subject, you can make this the subject by dividing by the current both sides. If we divide by the current both sides, that means we are left with the resistance across the shunt resistor in this case. So the resistor across the shunt resistor, it's IM times RM, which is the current across the meter times the resistance across the meter. So that is the current of 1 times 10 to the power of -3 for milliamps. So this is going to be 1 times 10 to the power of -3 times RM, which is the resistor of the meter, in this case of 100 ohms. So you're going to multiply by 100 everything over ISH, which is the shunt current in this case. And you're given that it must measure a shunt current of what? Of 10 amps. So we are going to divide everything by 10 in this case. All right, so that is going to give us the shunt resistance in this case. All right. So from this part, that means our shunt resistor is going to give us something like 0.01. So that's 0.01 ohms. You can convert to milliohms. Remember, milli is times 10 to the power of -3. So to convert to milliohms, you multiply by the inverse, which is times 10 to the power of what? Times 10 to the power of 3. So if you multiply by 10 to the power of 3, your answer in this case is going to be 10. That is now in the milliamps. So it is going to be ohms, sorry. So that's 10 milliohms in this case. So you can have it this way, or you can just leave your answer as 0.01. All right, so that's our shunt resistor in this case. Then we are now given to draw a circuit diagram to show how the shunt resistor must be connected to the measuring instrument. So this is the one that I was trying to have a sketch here. So you can just complete now to have it as a proper diagram. So how do you connect a shunt resistor in this case? So we saw that we are having our meter in this case, and we are given the shunt resistor that is now connected in what? In parallel to the circuit. So this is your meter, then this is the shunt circuit. We have got our shunt resistor. So here you are going to have the resistance across the meter, then the current that is going to flow across the meter, the current across the shunt, then definitely the total current flowing into the circuit, and the current at full scale deflection in this case, which is equivalent what? Which is equivalent IM. So that's how you can just have your diagram like just simple like that, guys. This is how many marks? 2 marks if you had to check. Isn't it 2 marks? Yes, just 2 marks. Just look at this, guys. 2 marks. Okay, so just leave it like that. Okay. 3.33, draw a circuit diagram to show the correct way to connect an ammeter in an electrical circuit. An ammeter is a device that is used to measure current, so it must be in a series circuit. So if I am given a voltage source in this case, let's say I have got a resistor in this case here, so I can just connect my ammeter in series. Okay, so this can be my ammeter like this. So you just draw any series circuit, any of your choice. So this is your ammeter here, this is your voltage source, this is your resistor, and that's the current in this case. So that's what we have, guys. Okay, so as long your ammeter is in the series combination, then it's fine like that. Okay, so that's what we had in this case for this one. Let's check the other part of the question on 3.4, where now we are given an amplifier with an input of 100 millivolts produces a current of 1.5 in a loudspeaker with an impedance of 8 ohms. Okay, so the amplifier, we are given its input voltage. All right, so we are asked to calculate the gain. Okay, so let's just take the information that you're given. So we have got the input voltage in this case. All right, so this is our 3.4. So you can just take our information here. So we are given the input voltage to the amplifier, which is given as 100 millivolts. But what is happening is that this amplifier that is having 100 millivolts, it is producing, to produce that, we now have the output from there. So we are having an output current and the output resistance, which means on the speaker, a speaker is an output. So we have got the current of 1.5 and the resistance or the impedance of 8 ohms on the output. All right. So on the output path, we are going to have the output current of 1.5 amps. So we've got 1.5 amps, and the output impedance in this case across the resistor, across the speaker of 8 ohms. The speaker is an output device. Okay, so the question is for us to calculate the gain of this amplifier if it has an input impedance. Take note, we have the input impedance of 300 ohms. So we are now given the input impedance of 300 ohms in this case. So the question is for us to calculate the gain. So we are going to have gain. If you are to check here, we can have power from this. So we can have our gain from power, which is given by the formula 10 log P out. So this is going to be P out over P in. So that is what you're going to have in this case. So that means from the information that we are given in this case, we can calculate the output power, the input power from the input values that we have. How can we calculate the input power from voltage and resistance given voltage and resistance? What is the formula for power? So that is what you ask yourself. So power is voltage squared over resistance. So this is going to be input. That is the input voltage of 100 millivolts. Milli means times 10 to the power of -3 squared over the total, over the resistance, which is the internal, the one that is entering here, the input of 300. So having the input resistance and the input voltage, calculating input power, we can have this as it is giving me 1 over 30,000. It was going to give us a decimal with a lot of zeros. So to avoid that, I'm just going to I'm preferring to work with this as a fraction like that, or you can write it times 10 to the power of -6 or whatever that you want. But as for me, I'm going to prefer writing it as like this as a fraction. Okay, so I have the input power in this case. So the question is, what about the output power? What am I given? I'm given current and resistance. So from current and resistance, how can we calculate power? We know that power is equivalent to I squared times resistance. So this is for the output. So that means our output current of 1,5 squared times the resistance of 8 is going to give us the output power in this case, which is 18 watts. All right. So I have the output, I have the input. Therefore, I can calculate the gain from this power that I'm given. So therefore, my gain is going to be 10. The logarithm of P out, which is 18, that is our P out, over P in as a fraction. I got this as 1 over 30,000. So I'm just going to combine this as a fraction like this. All right, so this is what you're going to have, guys. Make sure that you simplify properly from your calculator. That means your gain in this case is going to be something like 57,3239 and so on. So if you round off, it is going to be 57,324 in decibels. So that is what you're going to have in this case. Okay, so I just hope everything, guys, you saw that you need to work with the power. So you must calculate power from the input and power from the output conditions that you are given. All right, so that was the question. I just hope everything is clear. Then on question 3.5, we are now asked to define the term decibel, and it's 1 mark for that. Okay, how can we describe or how can we define this term decibel in this case? Okay, so I want you to see the definition that I'm having here, that a decibel is a unit used to measure the intensity of sound as an electrical signal, or the decibel is a logarithmic way of expressing the intensity of sound, that is the loudness. So that is how you can define this one. Okay, so that's it, guys. Let's see the other part of our question, which is now on question 4. So question 3, we are done. Question 4, draw and label the characteristic curve of a Zener diode. So you're given to give or to draw the characteristic curve of a Zener diode. So this is what we have in this case. We are given our Zener diode. So you can even mention these values, that's your VZ, which is your Zener breakdown voltage, everything IZK, which is your Zener test current, IZT, which is your Zener knee current, IZM, which is your maximum Zener current. So that is what you can just indicate from this part. Okay, so that was our question. 4.1, 4.2, state 3. We are given to state 3 properties of a Zener diode. What are the properties of a Zener diode in this case? Okay, so the properties of a Zener diode are, when used in a reverse bias mode, it had the ability to maintain a constant voltage across its terminals and current to flow in the reverse direction, that is cathode to anode. When used in a forward biased mode, it acts as a normal PN junction diode and allows current to flow in the forward direction, that is anode to cathode. When reverse biased, a Zener diode does not allow current to flow initially until its Zener breakdown point is reached. At this point, the voltage across the Zener diode remains constant. So that was 6 marks for these guys. Okay, so I just hope we have this complete. 4.3, we are given that a transistor output characteristic curve shows 3 regions. Okay, there are 3 regions on a transistor. So are now given to name and explain each. Okay, name and explain each of these regions that we have. Okay, so these are the regions that we have. We've got the cutoff regions, means the emitter base is not forward biased. Then we've got the action or linear region, means its emitter base junction is forward biased and base collector junction is reverse biased. And also we've got the saturation region, which occurs when the emitter base and the base collector junctions are forward biased. Okay, so I think this part is also much clear. Draw a circuit diagram showing a transistor as a switch. That is our question 4.4. We want to see how a transistor is drawn as a switch. All right, so this is what we have in this case, our transistor as a switch. Okay, just that my diagram is that ugly. Okay, but that's what we have, guys. I just hope it's clear for us. Okay, I'll try to have a better presentation next time, having better diagrams, but I just think it can help us. Okay, so that was actually 20 marks, question 4, guys. Okay, just your theory part. So this theory, guys, I advise you to revise much as you can. All right, question 5, you're now given to compare the 2 types of thermistors. Okay, remember we've got thermistors, that is the NTC, then the PTC. So we are given that by drawing and labeling their characteristic curves on a single graph. So you're supposed to give this on a single graph in this case. All right, so this is what we have in this case. So that is for the NTC, negative temperature coefficient, and the positive temperature coefficient, which is increasing with the resistance. And this one is decreasing with the increase in resistance. All right, so that was our question in this case, just to draw the diagram. And 5.2, by means of 3 labeled diagrams, show the construction of a bimetal strip. Clearly show the construction of the bimetal strip in a heated state and the bimetal strip in a cooled state. All right, so we need these 3 regions in this case. Okay, so in this case, I've got this one, the brass steel in a normal state. Then in a heated state, it's going to be a curve this way. Then when it is cooled, it's going to bend the other way. So that is, these are the 3 states that we have got in this case. All right, so let's see the other part. We are now given on 5.3 that give 5 applications of synchro systems. Okay, we talk about synchro systems in this case, 5 marks for that to give the applications. All right, so on the applications that I'm having here, we are given that it is used on the control of power tools, control of spaceships, control positioning of gun turrets, remote control of model cars or model aeroplanes in this case. Also, it is used in the application of this one for welding machines also. So you can even add another one for welding machines. All right, for welding machines in this case. Okay, that is to make it 5. Okay, so if there are any other points, guys, let us know on the comment section. Please assist us with more points that can help another person. Define Lenz's law. That is 2 marks to define Lenz's law in this case. And we have got this definition for Lenz's law to say that it states that when a magnetic field cuts through a coil and induces a voltage in a coil, causing a current to flow, that current will in turn generate its own magnetic field, which opposes the original inducing magnetic field. So that's our Lenz's law in this case. All right. The other part, which is our last part of the question, we are given now to draw the schematic symbols for a synchro transmitter. 3 marks for the symbols that you can have, the schematic symbols. Okay, so there are so many that you can actually have in this case. So let's just check 1 or 2 of these that we are given in this case. So like what you are given. So you can just, okay, there are so many. I've got, there are 5. So the most important 1, 2, A, B, C, and D. Okay, so but you can even take everything there. All right, so these are the symbols that you're going to have in this case, and make sure that you draw your symbols properly, guys. Your presentation must be properly drawn so that the marker is seeing what you're doing. Okay, so that was a total of 100 marks in this case. Industrial Electronics N2 from Mason African Motives, working on netted engineering till we meet again. So let's try to revise, guys. For those who are to write in August, let's be revising. For those who have written now, you can see that, okay, this part and this part is fine. Then you can even calculate your marks to see, okay, is it possible for you to continue, or you can work on a rewrite for the next trimester. All is fine as long we are doing it in a proper way. Okay, so that's it, guys, from Mason African Motives. Till we meet again.